Also, just quickly before I start, I would like to mention Enrico, who was my second supervisor. He died in October last year, so I'd just like to salute him and be grateful for all he's done for me. And so, I think a lot of you might have known him here. Right, okay, so I'll start. Humidity buffering, just to make sure, a little introduction, and make sure that we have the same vocabulary and we understand, we talk about the same thing. So what I understand by humidity buffering is the potential to absorb humidity from the indoor environment when it's in excess and restore it under dry conditions, so it doesn't dehumidify, as sometimes I've heard, or it's just like a big storage capacity. It stores the humidity and it releases it when the relative humidity is lower. So this applies for any porous hygroscopic building materials or breathable materials, as someone has talked before. So porous hygroscopic building materials, a lot of sort of hemp, organic fibres that are very hygroscopic, and particular clay minerals. It's a natural process. We don't have to do anything to the material, so it actually acts as by itself. So all we can do really is optimize its performance in the building. So that's a quick table just to explain why it's important to get stable relative humidity in the building. So he shows here that with a high relative humidity, and what I call relative humidity is the vapor concentration on the saturation vapor concentration, so it's a percentage. So here, at high vapor relative humidity, you can see that, for example, there's a lot of increase, there's an increase in microorganisms like dust mites, viruses, bacteria, and also at low relative humidity you get trouble with respiratory infections, allergies, asthma. I think asthma is probably one of the main concerns in England because it's the world leading country of people suffering from asthma, 15% of the population. So there's an optimum zone that has been identified between 40 and 60% relative humidity. So my work, I haven't done that much. I can't, for example, predict, well, this earth ball is going to stabilize the humidity to 50% relative humidity. My work was really on the material itself, try to understand how it actually acts, how it absorbs this humidity, and how we can try and optimize it. And because the earth materials are there's a large variation, so one material to another is actually quite different in this behavior. So the benefits, what we can get from that is stabilizing indoor humidity levels, health benefits for the occupants. Also, it has been applied in archive storages. So Hatfield has done a lot of work on that and tried to, for the conservation of books or artifacts. And because often these archive storages have a very high bill of trying to maintain stable humidity. So this could be used instead. So reduce surface condensation and therefore the mold growth on the surface. Reduce the energy consumption of mechanical indoor climate control, so insulation or dehumidification, so this has been mentioned before as well. And I totally agree on that the soil actually can also bind pollutants. So there is studies, not in civil engineering, but more in chemistry, where they actually do sorption isotopes with volatile organic compounds. So the soil absorbs volatile organic compounds exactly in the same way we do with moisture. So if there is an increase of a certain concentration of a pollutant, the soil actually binds it to the clay minerals. So what we've understood so far from the process, what's going on in the soil, so that's a wall fiber, but it's just to show the surface absorption. So there's two main processes, the surface absorption and the capillary condensation. So at initial stage, at low relative humidity, you have, that's what we call it, a monomolecular absorption, so there's a layer of water, like molecules of water on the surface, multi-molecular absorption, there's several layers of water, and then the capillary condensation starts when the pores actually fill in. And this is around 60 to 80% relative humidity, depending on the material. So that was just to illustrate the wool fibre on the right. So under dry condition at 95% relative humidity, we see the water layer forming on its surface. So it doesn't actually need pores to retain the water. So what we've been doing mainly is trying to measure this performance, and that was done what we call dynamic moisture absorption, or it's known as the moisture buffering value. So the experimental setup we've used was mainly following after a project in Northern Counties, so it's called the North Test project. And basically, so we put a sample on the scale in a climatic chamber, and then we vary the input signal of, well, the temperature stays constant, but we vary the relative humidity. So we change the cycles from high relative humidity to low, and we see how the material performs, how much moisture it actually absorbs. This is given by the scale, so it is in grams per square meters here on the right. And then we can test different samples, so we test it, stabilized samples, cement stabilized, and we can see how it behaves, if it absorbs more moisture or less. So the first thing we had to do as well is try and have a look at what actually in the experiment would have an effect as well on this value. So there's a paper you can have a look at. It's now so for example, the air velocity in the chamber, how that influences the readings, different relative humidity cycles, different time steps, different logging methods, so this is all in there. So once we knew exactly what we were measuring and how we can get reliable results, we started doing a series of samples with different material properties. We could analyze the data. But, this is just the different properties affecting the moisture buffering. So what we identified. So of course there's the water vapor permeability, and we often refer to as water vapor resistance factor. So this is basically the speed at which the vapor can transmit through the material. And then there's the moisture capacity, which is the slope of the absorption isotherm, and this is the storage capacity. So these, as an example, there's two different clay minerals. So there's kaolinite and marmoronite. Marmoronite is a smectite type, and its moisture content in percentage per relative humidity. So you can see that the two behave completely differently. So most of the samples, most of the soils are probably more like the kaolinite at the bottom. But there is a variation between these different clays. Surface film resistance, that's directly related. We assume that's directly related to the air velocity in the chamber. So we don't actually know if there is a difference of surface film resistance depending on the material, but I haven't found anything that relates to that. And it doesn't seem likely. So, yeah, now I'm just going to go through a lot of, sorry I haven't got any pictures, I just got graphs and figures. And values. So yeah, so as I said, we did different samples with all kind of different properties. We tried to keep the same properties and just change one property at a time. So for example, the compaction water. So I worked mainly on compressed earth blocks, but I believe that because these properties are the same for plasters or adobe or rammed earth, they would have the same effect on other types of building materials. So for example, compaction water, so the black dots are the moisture buffering value, and you can see with an increase in compaction water, the vapor resistance increases and the moisture buffering value therefore decreases. This is very likely because the compaction water also has an effect on the density of the material. And because the density, that's one of the main properties that affect the vapor resistance. So that's clearly, you can see the relationship between these two properties. So again, black is moisture buffering value, it's decreased, vapor resistance is increased with the density. So that was an interesting result because we added, with some samples, we added a certain percentage of SMEC type. And in this case, even though the vapor resistance increases, which would normally decrease the moisture buffering value, actually it is the other way because the storage capacity of the sample is increased, so you actually have more storage. And this is with very low percentage SMEC type. So we didn't have any swelling problems with our samples or shrinkage. Stabilization, so we tried different contents of cement, lime, 4% of lime, 4% of cement, 8% of cement, 8% of lime. Geopolymer is quite trendy at the moment, adding sodium hydroxide to the soil. And they all decrease the moisture buffering value. So there's some papers that say the opposite, but all our samples showed that the dynamic response is decreased. That was just to illustration. We don't actually manage to get any sort of valuable information out of that. It's just to show that the different textures we got in our samples, high density, high water content, or low density, is always macro porosity, like what we can see on these pictures, is very important for the vapor permeability. And that's probably where adding organic fibers is very interesting because it opens the structure and the vapor permeability is increased. So just an overview of what the samples I've shown here is, so there's not much in the literature that you can really compare it to because it hasn't been done that much in moisture buffering values, even though there is actually an international standard to measure the moisture buffering value. The NOR test, there is a Japanese standard, there's a German standard, but there's not that much reference, especially not for earth building materials. So I still compared it to the NOR test, the results they had for concrete, gypsum, laminated wood, etc. There's quite a few different, and these were sort of averages they made over 3 or 4 different laboratories, different universities. So the soil shows that it has very high moisture buffering value compared to all the others. But what is noticeable with the soil is that there's very large variation. So depending on the material density, all the material properties, it can have actually quite a difference. I think we understand now clearly enough to be able to design materials that are more in the very high value of moisture buffering value rather than at the bottom. So conclusions and maybe just some information that can be easily taken home, sort of. Well, ways to improve moisture buffering, what we've noticed so far is reduce water compaction, keep a low density, so low vapor resistance, and the addition of sweating clay, SMEC types, water stabilization, and keep an open structure, so high microporosity, and addition of organic materials. That's actually also something we want to look at. So this is an ongoing work. We're actually going to measure exactly the same way. So vapor resistance, moisture buffering, and absorption isotherms on plasters, and addition of various crop wastes. I haven't done hemp because I know some people are working on it. So we're looking at different organic fibers and see how that behaves. Yeah, that's it. And I'd like to thank Pete, who's head of the department at university, Mike Lawrence, who's part of EBUK, Andy, my supervisor, Dan Maskell, who left, I think. Neil, who's a colleague, he was actually studying at CAT as well. So, voilà.